Alright guys, I've been trying to find time to do this video for you. A lot of people have been asking me for it, so I'm going to try to get the information through this video as quick as I can so that I'm not taking up a lot of your time, but you have a vast bit of knowledge in such a short period of time. So I'm going to try to cover as much as I can. If you have questions, I'll do additional follow-up videos as necessary to answer those questions if I can't do it in the comments. So, how to choose the right cylinder head and cam for your intended application. This is a very hard subject for a lot of people because they don't necessarily understand exactly dynamically what's happening in the engine. And there's a lot of marketing fluff out there to try and say stages, stage 1, stage 2, stage 3. A lot of that's nonsense, and I'll prove that to you today. So, what is the application? First thing you got to do is choose your application. So, what's it going to be used in? Towing, a street rod, circle track, drag racing. How heavy is the vehicle? All that needs to be known prior to choosing a set of heads in a cam. Once an application is chosen, ask yourself how much horsepower you want to make. For example, say you want 500 horsepower at the crank. Assuming 100% volumetric efficiency, and if you looked at one of my last videos, I kind of helped you determine what your rough volumetric efficiency probably is for your application. So look at that video if you want to know. Follow this formula. Okay, so I just threw an example out here. So desired horsepower potential divided by 2.08 equals required average head flow in 28 inches of water. Okay, so average head flow, I'm going to get into more detail, but that is key, that is important. Okay, so here's an example. If I want 500 horsepower, so divide that by 2.08, and I got 240 CFM at 28 inches of water. And that is average head flow, okay, not peak head flow, and I'll get into that here shortly. I put a note here. Typically, a street car has a volumetric efficiency of around 85%. Some are as low as 75%. Just keep that in mind. To get the desired horsepower above, this will need to be improved with the right piston design, right compression ratio, high coefficient of discharge, all those good things. Okay, supporting parts are important. If your heads can flow a certain amount, but you have a restrictive intake on there and it doesn't even allow it to flow that much, it's not even going to get that much. So you're going to not see the full, full horsepower that you could have got. Also remember that the rest of the combo needs to be able to support. Okay, that's all I'm saying. Cubic inch, intake manifold, carb, throttle body, air filter, camshaft, etc. Okay, everything going in and going out needs to be able to support the flow that your camshaft and your cylinder head can develop together. So a head and cam should always be chosen together. You can choose a head if you already have a cam, and choose a cam if you already have a set of heads, but it's best if you're choosing for a custom application to do them together. And if you have someone who's porting your heads, they should give you a recommended cam for that cylinder head for your application. If they don't, then I would not go to them. So 3, now that you've chosen a target power number, it's time to choose where you want that peak power to happen. Use the below formula to estimate the required average head flow to get to the target RPM. You could also rearrange formula to solve for peak power RPM given a known average head flow from the formula, or solve for the required cubic inch diameter to meet the desired power number. Okay, so algebra is algebra is algebra. You can rearrange formulas all you want and solve for the unknown, right? So just for an example here, desired peak power RPM. Just so out there, I do not own any of these formulas. These are just kind of knowledge gained from reading books and testing on the flow bench myself and real-world applications. So I don't trademark or say I own any of these formulas, so don't try say I am. So anyway, so desired peak power RPM equals 1196 divided by engine displacement divided by 8. So basically, the displacement of a single cylinder, 1196 divided by that, multiplied by the average head flow in CFM. That's going to give you the peak power RPM at which it's going to make the power that you're wanting. So this 500 horsepower here. Okay, so let's go through our example here. At 6,500 RPM equals 1196 divided by 350 cubic inch, just a small block 350 divided by 8, equals X, or X equals, just rearranging the formula here, X equals 6,500 divided by 27.34, or 237 CFM, okay? So that's going to be pretty close to this 500 horsepower, 237. So here's my note. What this formula is telling us is we would need an average head flow of 237 at 28 inches of water to make roughly 494 horsepower at 6,500 RPM on a 350 small block Chevy. Again, this is assuming 100% volumetric efficiency, so the results will be closer to 420 horsepower at 85% volumetric efficiency at the crank, assuming the rest of the combination supports it. So a lot of words to basically say 420 horsepower from a 350 small block at 6,500 RPM is very realistic, and that is a very real number. Most of your applications, basically, you have a 420 horsepower if you have all the supporting modifications. The camshaft has to be correct for the cylinder head to make this average head flow, and your intake and your exhaust cannot be restrictive. I'm going to go into more detail about that, but again, if you have any specific questions about your application, just put them in the comments. Alright, the next step is to find a set of cylinder heads that have the average head flow that you need, and the camshaft that will allow for that max flow potential with the lift, flow potential, and duration, RPM potential. Keep in mind, the flow I'm talking about is average flow, not peak flow. Just because a set of heads flows 300 CFM at peak valve lift does not mean they will support 624 horsepower, as the formula would suggest. Because this is peak flow, not average flow. The formulas do not consider frictional, thermal, or other losses either, but they will get you really close, and they do get you very close. Keep in mind, red bold, there are also other considerations to make max power potential than head flow alone, such as minimum port cross-sectional area in the head and port volume, which will be discussed next. Lastly, the average head flow calculated must be with everything bolted together on a flow bench at 28 inches of water. So, for example, I did a video of flowing a set of heads with my blower manifold on it. That's pretty close, but I also need to put I couldn't mount the blower on there, but if you're just doing a naturally aspirated setup, it's easy to put the intake on there, the carburetor on there, and the air filter on there, and that is going to get you the best flow numbers, okay? And that'll tell you, flow the heads by themselves, flow it with the intake manifold on there, see how much it drops, and then put all that other stuff on there and see how much it drops. It will surprise you at how restrictive a lot of the combinations out there are. It is very important that when you're doing these flow tests, you don't just flow the heads, because you can have a great set of heads and destroy them with an intake manifold. So here's a very dramatic picture. Okay, this is not exactly how the dynamics work, but it's very, very close. Okay, so we have just an example here. Okay. And I put here, typically the average flow will drop significantly unless each component is optimized for the head capability. You will only flow as much as the smallest port. That's fact. For example, see the below two drawings. It shows the significance, port size, volume, shape, etc. Okay, so first picture here, I've got a carb, and intake manifold has very sharp corners going into your runner. This is very indicative of like a dual plane kind of design. Some of them have this sharp corner here. Some of your single planes have very sharp blades separating the individual runners. Those kind of need to be rounded off. But so the air is going to come in, and there's going to be some turbulence here. But so air does not want to change direction. It has momentum. Okay, it has mass and momentum. So you're trying to turn air, and the way you do that is with differential pressure. But without getting too in depth on that here, just showing you, you have a skinny port here, you have turbulence here, the air is going to speed up really fast coming in here. Then you have this sharp transition, okay? Air is not going to want to bend around this. It's got mass momentum. You just sped it up by putting it into a tiny port. You got this big volume here, and you put it into a tiny hole. What's that do? It speeds the air up. Well, when you try to speed the air up and turn sharp corners, it doesn't want to do that, okay? It's got fuel with it too. You have some shear that's going to happen here, and you're going to have deatomization of your fuel. You don't want that. You want a very smooth transition here. You don't want the air to have to work. Again, this is a very, very common angle of approach in some of the aftermarket intake manifolds. So whenever you do this, when you port your heads, make sure port matching is not so important, but making sure that transition is as smooth as it can be is very important. So if you need to lift the roof up and not widen it so much for volume, you can raise the roof and raise your intake manifold to make this a smooth transition. Very important. Alright, so you're going to go around and through your intake valve. Okay, so again, over here a little bit more optimized. We lowered the floor, we pulled the floor back. Okay, this is going to slow the airspeed down, but that's okay. Air's going to come in. It's kind of a smooth transition to get to the intake valve. Okay, we're still, see how it's a tapered runner? This is the best way to do it, is a gradual taper from the beginning of the runner all the way to the valve, is a slight taper going bigger, smaller, smaller valve. You don't want to go big, small, big, small, big, small, and then you have different pressure drops, and the only time you kind of want to do that is right here on the bowl side. You usually make this a lot larger to slow the air down and allow it to make this turn so you don't shear off the back of the valve. You have a gross imbalance of flow around the whole perimeter of the valve when that happens, and it pockets over here. And you have a lot of airspeed here and a lot of turbulence, and you just have no flow. And so you have a gross imbalance of flow around the intake valve. So you do want to make the bowl larger to slow the air down to get it around the short term, but there's a little bit more of a detailed conversation with that. So once you have chosen a peak power, let me check my camera, make sure everything's good with it. So once you've chosen a peak power RPM, now a set of heads, it is time to ensure the heads you chose can support that RPM. The two major considerations is minimum cross-sectional area, okay, minimum port cross-sectional area, smallest area in the port, minimum cross-sectional area, pinch point, or smallest area in the port, like I said, and total port volume. So if you get the minimum cross-sectional area correct and you get the velocities all correct in your head, the port volume will be a derivative of that. It'll already be correct. You just make that point now. However, if you are not porting the heads and you're just buying heads, port volume is important, and we'll look at that. The reason it's so important is because it's an indicator of how much RPM the heads can support before air-fuel mixture quits increasing and becomes very turbulent. Use the below formula to estimate the minimum cross-sectional area for the head. Okay, so basically what this is saying is you're speeding up the air, right? If this area around the push rod, which is usually where your minimum cross-sectional area is, it's the smallest area in the port, is around the push rod on a 2-valve push rod type cylinder head, wedge head. If this is too small, you're going to have big taper, and it's going to get real small right here. Your airspeed's going to go up, you're going to have a pressure drop, and it's going to increase in size, right? There is a point in which the airspeed gets so fast that it becomes very turbulent, and you'll have a point in time where you always go from a high pressure to a low pressure, and with the volume decrease, pressure goes up, volume goes down, right? So the pressure in here is going to get to a point where it's higher than the pressure upstream, okay? And when that happens, you will not have any more flow, okay? flow always happens from a difference in pressure. So high pressure to low pressure. Always remember that. So you can get to a point where the pressure is so high right here at the pinch point that you will no longer flow. Okay, so that is very important that that minimum cross-sectional area is correct, or you will never reach the RPM that you want. You just won't. And you'll spin that RPM. You can always spin the RPM. Your engine will always go that fast, but it will not make more power. It'll just fall on its face, and you'll start breaking parts. All right, so just remember that. So we're going to take minimum cross-sectional area equals, okay, this is a parentheses. You take your bore squared times your stroke times peak RPM that you intend to run divided by 190,000. Okay, this is going to get you pretty close. So here's an example of 6,500 RPM small block 350 that we talked about. So you got a 4-inch bore, 3.48 inch stroke, 6,500 RPM. Okay, this is our 500 horsepower deal that we were talking about. 190,000, or a minimum cross-sectional area of 1.905 inches squared. Okay. When you're buying a set of cylinder heads, I know AFR will tell you what the minimum cross-sectional area is, and some of the other manufacturers will as well if you just call them and ask them. But this minimum cross-sectional area, this is pretty similar to like a set of AFR 195 heads. That's pretty close to what their minimum cross-sectional area is. Note, what this means is that the smallest area in the port must be no smaller than 1.905 inches squared to support 6,500 RPM. Keep in mind, changing the engine displacement changes the requirements of the minimum cross-sectional area. Okay, for example, if you were to change it to a 383 cubic inch engine, you must now have a 2.084 inch squared to support the same 6,500 RPM. Okay, so this is like an AFR 210 head. Okay, it makes sense. You have a bigger engine, you need more air. Okay, more air, you need more area. Okay, it's very intuitive. But just so you know, this is closer to a set of AFR heads. I think the AFR 210 heads have a 2100 cross-sectional area. This is why it's not always the biggest head that makes the most power. What makes the most power is the right head for the combination. Okay, so if we needed a minimum cross-sectional area of 1.905, but we put a set of, and let's just say AFR 195 heads were the right heads, but we put a set of AFR 210 heads on that same application, okay, we could support more RPM on the same cubic inch engine, yes. However, if your flow if the cylinder head flow does not support the higher horsepower, then spinning it up higher doesn't make any more power, and the airspeed is going to go down because the port is getting larger, and so that's going to hurt low end torque. So you're going to get to a point where the head is too big for the application, for the cylinder head flow in the camshaft, so that you are losing torque down low and you're not making any more horsepower up top. Okay, so a bigger head is not always the best option. Okay, so we'll squash that right here. So this is why it's not always the biggest head that makes power. Okay, it's the right head. That's why we're doing this video. Okay, not necessarily the only other important factors, such as importance of different combustion chamber designs and intake and exhaust flow ratios, but the last thing I want to discuss for now is the significance of port volume. Typically, if you get the minimum cross-sectional area and average flow where you want it to be, the total port volume and cc's will match what you need as simply a derivative. Okay, so that's what I said earlier. If you get everything, the localized velocities right and your minimum cross-sectional area right, typically the port volume is a derivative of that and it's going to be correct. However, if you want to check to ensure you're in the right ballpark, simply multiply the potential horsepower determined by the above formula by 40%. For example, using the same 350 small block Chevy example as above, we would need a 237 CFM at 2.08, which is 494 horsepower. Multiply that by 40% and you get 197.83 cc. Next, compare that to the heads that you've chosen. For example, either a 195cc or 200cc head would be appropriate. It is always better to caution on the side of smaller, as the larger the head, the slower the port velocity. On a boosted application, port velocity still matters, as you are not forcing air into the port as everyone in the world seems to think. As some people seem to think, but that is all I hear people say is when they put boost on it, it doesn't matter about velocities and cylinder head and all, port volume and all that. Doesn't matter because I'm forcing the air in. You are not forcing the air in, okay? I'll get into this later. All you are doing is changing the density of the air that is flowing. So you are still going to flow 237 CFM, but instead of only 21% oxygen at sea level, you're going to increase and generate an artificial atmosphere. So you're still flowing 230 CFM, but there's going to be additional oxygen available for burning more fuel and making more power. Okay, all you're doing is changing the density of the oxygen molecules available to burn, to facilitate burning. Alright, now that you've chosen a set of heads, it's time to match a camshaft to maximize that head flow potential. Okay, so all that was kind of choosing a set of heads. It's not the only things that matter, but they're most important things. One other thing you can do before you get more in depth is you can find the average flow of your existing heads, estimated of course by taking the average of each flow at each lift point, assuming you have a flow bench numbers from either a local shop or the manufacturer. Below is an example of a set of small block Chevy Eliminator CNC ported AFR 210 heads with an estimated average flow number. These heads are advertised to support 6,500 RPM on a 400 small block Chevy. The minimum cross-sectional area on these heads is 115 square inches. So I said 100 earlier, it's pretty close. And looks to be very close to recommended value per the formula. Okay, so we took, to make a 400 small block Chevy is a 4125 bore, a 3.75 inch stroke. Okay, multiply that by 6,500 RPM, divide by 190,000 is 2183. Okay, and again 2183, 21815, those are very close. Okay, one question you may ask yourself is, why is 100 thousandths lift not here? Okay, I'm gonna tell you why it's not here. Alright, let's pull up. This is Old Red's engine. Okay, let me make sure you can see this. I'm gonna hold this camera up for a second. Actually, I need to sit it down. Let me turn this so you can see. Alright, so this, just hold. Alright, so this is the engine. Alright, so this is my camshaft, my cylinder heads in Old Red. This is exactly what it looks like at 6,300 RPM. Alright, so I'm gonna stop it here and let's go back. Alright, so the intake valve is open. Let me close the intake valve real quick. Okay. Okay, so the intake valve and the exhaust valve, we're in overlap right now. The intake valve and exhaust valve are both open. You see these arrows, they're kind of showing velocity, and your velocities are here and here respectively. Okay, so what I'm going to show you is why we don't care about 100 thousandths lift flow. Let's put the piston at exactly top dead center. Okay, so the piston is at top dead center. The valves are both open almost exactly. The intake and the exhaust have almost the exact same lift value. Alright, so actual lift at the valve is 94 thousandths on the exhaust and 97 thousandths on the intake. Okay, that is 100 thousandths. Why do we not care? Well, the exhaust valve is open exactly the same amount. Okay, we are taking the inlet charge and we are helping scavenge the rest of the exhaust gases and the burnt fuel gases and everything that needs to get out the exhaust. So right now, during overlap, we are helping scavenge the cylinder. We are not using this flow to make power. Okay, so let's go forward a little bit. Okay, exhaust valve is now, we go to where the exhaust valve is closed. Okay, exhaust valve is now closed. Okay, we're at 300 thousandths on the intake. Okay, but the piston's already moving down the bore, so we are using that flow for power. So pistons at top dead center, we're at 119 thousandths on the intake, not using this to make power. Exhaust valve's closing. Now the cylinder's going down the bore and drawing in that into inlet charge. This is where we're using to make power. Okay, we were at 100 thousandths lift. We were not using that. We were not using that for power. Okay, so don't use it in your formula. Don't use it in your calculation, because it doesn't matter. It doesn't mean anything. Okay, that's why they don't tell you this, but that is why they don't provide 100 thousandths lift values. Let me take a drink here. That's why they don't provide you 100 thousandths lift numbers. It doesn't matter. You're using that to scavenge the cylinder, and that is it. Okay. All right, going back to this. Let me fix my camera here. All right, back to this. All right. So AFR, these are just the values that AFR posts out there. Now this is not 100% perfect. I'll explain why after I read the note. Look at how this looks to be looks to be too big for our 500 horsepower, 6,500 RPM, 350 small block. This has a 2,115 minimum cross-sectional area. So in actuality, they would be a better fit for a 383 or a 400 cubic inch engine. Below, we will discuss how to get more accurate average head flow number, as the camshaft load profile can be altered to fit different RPM requirements. That is key. Okay, this is why picking the right cam for the head is important. On the same set of heads, different camshafts can move your average flow. Okay. Notice that they do not provide the 100 thousandths lift. Why? This is due to the position of the piston in the cylinder at top dead center during valve overlap. I just explained that. For all of you technical people that want to find the right camshaft to support this, now remember, I did that but I did this so that I could share this with people. Okay, this is I'm doing a video of it, and that's why I'm reading it to you, just try to keep me on track. So some of the wording doesn't make sense for a video, but bear with me. This is to choose the right cam to support the RPM and desired average head flow on a naturally aspirated engine. And I will also discuss boosted engines later. This is where it all gets a bit technical, and to be successful in designing a camshaft, you need to understand the valve events and their individual significance. The typical intake and exhaust duration advertised in catalogs is the derivative of choosing several individual points. That's why you can have two camshafts with the same duration, but act completely different and make different power. Okay, and I'll get into that and why that is. Which camshaft for the application? Excuse me. Let's look at some of the important points. Okay, exhaust valve open point, relatively least important, but needs to change related to the type of aspiration and time required for exhaust scavenging. For example, if you're running boost, you tend to need additional time to get the exhaust out before the intake valve opens. It makes sense. You're burning more air and fuel. Okay, you just are. So you have more exhaust gases. So the valve needs to be open longer to get the same amount of to get all that exhaust out. Opening the exhaust valve before bottom dead center early allows for an efficient exhaust scavenging, as the cylinder is still on the power stroke, and some of the energy that's left can be used to push the exhaust out of the chamber. Open it too early, however, and you will lose power potential from the stroke. This point can also be altered directly influence turbo spool. That is correct. You can actually open it earlier to help with spooling the valve. Spooling a turbo. But real quick, let me show you what I'm talking about here. So let's go back to our engine. Okay. I'm gonna hold this again. All right. So intake valve is opening. That the length of that arrow shows port velocity. All right, we're on the power stroke. It's spark plug just ignited. Okay, sorry, my camera overheated. Anyway, so bang, the spark plug just went off. Let me go back here. All right, see this yellow thing? That's just showing you that the spark plug has ignited. Intake valve, exhaust valve are closed. We're getting down here to what we were just talking about, the exhaust valve open point. So if you look at cylinder pressure, okay? When the spark plug ignited and the flame started going, okay? We have about 1,300 pounds of pressure in the cylinder. And that's quickly going down. So the exhaust valve starts to open here. Okay, there's only about 180 pounds of cylinder pressure left. Okay, and we're using some of that to evacuate the exhaust. Okay, so if you look here, look at the pressure in the exhaust, 27. Okay, 14.7 is atmospheric. So we're almost doubling the amount of pressure. There's no boost here. There's no intake valve open. There's no supercharger forcing air out. This is how much pressure of a pressure wave that there is inside of the exhaust. So what this tells me is until this equals 14.7 psi, we're going to have that arrow going really fast out the exhaust. So watch, pressure's coming down, piston's on its way back up. Now we're around atmospheric pressure, so there's a lot less velocity. Velocity's slowing down, starting to get a negative pressure because the exhaust valve closed. Okay, not negative, but less than atmospheric. Let me make that clear. Okay, so that's the significance of the exhaust valve open point, is we want to use some of what we have left in the power stroke to start to get that exhaust out. Okay, all right, and I think that is around 56 degrees before bottom dead center. So you know, it depends on what you want. Normal boosted stuff, you're around 60 degrees. This is at 50 thousandths. Okay, these are the set points at 50 thousandths lift. You're usually around 60 degrees to 65 degrees before bottom dead center on like a turbo deal or a positive displacement blower. More like 50 to 55 on a ProCharger or something around naturally aspirated. Okay, exhaust valve close point. Depending on the point chosen affects how much overlap you will have. This affects idle vacuum, idle quality, scavenging. Again, the amount of overlap needs to change with the application. On a boosted engine that makes relatively low boost, such as less than 15 pounds, you tend to want close to 0 degrees of overlap. This is because during overlap, both the intake and exhaust valve are open, so if there's too much overlap time, the boost will go straight out the exhaust and not stay in the chamber where you want it. You can still make more power with more overlap with boost, so 0 degrees is not always correct. This is important. If you notice, my application is supercharged. Okay, old red is supercharged. And I make less than 15 pounds of boost. I make more like 11, 12 pounds. Okay, so what's important to know is this is not a hard and fast rule right here. This 0 degrees of overlap. A lot of your factory stuff will have pretty close to 0 degrees or even negative overlap. Okay, this is good for a factory type vehicle. Overlap hurts idle quality. It's not good for a daily driver for what the factory's trying to get after. economy and all that kind of stuff. Now, on aftermarket deal, small block Chevy, old school wedge head type stuff, even the new stuff, overlap at high, it tends to favor high RPM power. Okay, the amount more overlap you have, you tend to be able to spin it higher in the RPM range, because for especially a naturally aspirated deal, the overlap, it helps with exhaust scavenging. There's wave tuning and all kinds of other stuff involved. We're not going to get into that right now. Intake valve open point, same as exhaust valve closed. Depending on the point chosen, affects how much overlap you have, which affects idle vacuum, idle quality, and intake reversion amount. Intake reversion, let me go back to our engine here and show you what I'm talking about for the reversion. So, if you look, the intake valve is open. Intake valve open. Okay, we're greater than 14.7 pounds of pressure because we're boosted. Alright, so if you look at that. Arrow went the other way. A very minimal reversion. Very, very minimal reversion. To the point where it's non-existent on mine. And I have programmed, I have ported it in such a way and picked the camshaft in such a way that I don't have really any reversion, but there's a very microscopic amount showing in there. That's basically when the piston's on its way back up the cylinder and the intake valve is still open. Okay, all cams are going to close after bottom dead center. However, the point at which the intake valve closes is what we're going to talk about next. The opening point is going to affect reversion a little bit too, but not super important for this. Intake valve closing point, the most important, okay? The most important. I know I say C.16 before moving forward. We'll go to that in just a second. Most important. Intake valve clove timing event. This dictates total cylinder pressure, which will directly relate to low and mid-range torque production. Closing the intake valve early builds more cylinder pressure, where closing the intake valve later keeps the valve open longer, allowing more time to fill the chamber. However, this is a fine line, and closing the intake valve too late will force intake charge back into the intake tract, losing power potential and lowering volumetric efficiency and shortening the effective engine stroke. To put this simply, closing the intake valve very early is good for trucks, heavy cars. Closing slightly later is good for high RPM street cars, and closing the intake valve much later tends to favor well in basically all-out drag racing deals. Okay, because you're going to have very, very poor low RPM torque. Purpose-built drag racing engines do not do well just to stoplight to stoplight. They just don't. That's not what they're for. They're for all out, all performance up on their stall, starting out at like 45, 55, 6,500 RPM. Okay, well inside their camshaft's power band. Okay, intake center line. Okay, so we're gonna get on more on intake valve close. Real quick, I guess we'll go to number 16 here. Let's go down here to 16. Dynamic and effective compression ratio. Okay, so there's mixed feelings out there about effective compression ratio and its applicability to all this, but it is applicable, and we're going to talk about it. This is a subject discussed very rarely, and when it is, usually disagreements happen. I'm going to give you my feelings on the matter and what I've seen. But it's still a real indication of camshaft performance on a given combination and should always be used. It's not the end-all be-all, but it is a point of measure that is significant to know. Everyone knows about static compression ratio that has ever touched an engine. However, not everyone knows the significance it has on having the correct dynamic compression ratio. The static compression ratio is typically matched to suit the expected fuel to be used, maximize performance without hitting pre-ignition detonation. Okay, the static compression ratio is not the full story, and like most things on an engine, is just part of the consideration. Okay, and this is just another one of the parts of consideration. This is where intake valve close becomes so important to get right for the application. Static compression ratio tells you what the compression ratio is when the engine makes full sweep up and down the stroke. However, the intake valve closing point typically comes after bottom dead center to take advantage of cylinder ramming and filling. Okay, again, what I said, air fuel mixture has inertia. So you have what's called inertial filling. It's ramming, it still has inertia. Even though the piston's coming up, there's a point at which the differential pressure, as long as the pressure inside of the intake tract, okay, we'll go back to the engine here, as long as the pressure inside of the intake tract, okay, we're going to back it up, intake valve, okay, look at the pressure here. As long as the pressure, 21.6, is greater than the pressure inside of the cylinder pressure, okay, it's 21.6. As long as this pressure is greater than the pressure in the cylinder, you will still have filling. Okay, so we're going, pressure is still 25.6, 26. This is the part, 26.7, 26, 27.2, 27, 28, 29. They equal the same amount right here. 30, 30. Okay? Intake valve is just barely open, guys. Just barely open. Okay? I designed this cam so that it would have the perfect intake valve closing point at my peak RPM of 6,300 RPM. Okay? Now, if you get this and make that intake valve close later, you're going to have what's called reversion, and your intake charge is just going to go right back through the intake. You get too big of a camshaft, which is what 900% of everybody does, is they want the camshaft that sounds cool, and they want it to just be big. But a big camshaft on the application that does not need a big camshaft is going to have reversion. And you're going to send your intake charge right back out the intake valve and back into the intake, and you are not going to have as much mixture in here, and when it ignites you will not make as much power. Okay, do not oversize your camshaft. Alright, dynamic compression ratio will kind of help you with that. It'll give you a good idea, but it is just a measurement. Alright, so back to this. Static compression ratio is typically matched to suit the expected fuel. Okay, blah, 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 blah. Alright, this is where intake valve close becomes so important to get right. Static pressure ratio tells you what the pressure ratio is when the engine makes a full sweep up and down the stroke. However, intake valve closing point typically comes after bottom dead center to take advantage of cylinder ramming filling. I already said this. Since intake valve close happens after bottom dead center, we are not taking full advantage of the stroke. This means we need to measure the actual compression ratio the engine is seeing. Okay, now naturally aspirated, this is more accurate. In boosted stuff, we're usually higher than 100% volumetric efficiency, so it's not as big of a deal. However, naturally aspirated, this is a very big deal. This compression ratio is directly proportional to the intake valve closing point. If you know the exact amount of stroke used after the intake valve is closed, you can simply replace that number in the standard compression ratio formula or calculator to get dynamic compression ratio. This number will always be lower than the static compression ratio, naturally. However, much lower, is what is important. How much lower? A typical naturally aspirated race engine needs a dynamic compression ratio of around 9 to 1. Okay, with our engines running a very late intake valve close point, this means a very high static compression ratio, greater than 12, 13 to 1. A street car needs a target closer to 7.5 to 8.5 dynamic compression ratio on a naturally aspirated deal. Normally around 6.5 to 7 with a boosted. With 8.5 to 1 being very high and 7.5 being a great target for pump gas street stuff. If the dynamic pressure ratio is slightly lower than 7.5, it is okay, but if it is less than 6.5, you are asking for a complete turd. You'll have no torque down low. This is the biggest mistake people make when choosing a camshaft, is over-camming their engine with a intake valve close point that's way too late. While the dynamic compression ratio will not tell you everything you need to know, it will tell you if you have gone too far in cam size. Okay, so that's all I use this for. It will tell you if you've gone too far in cam size. I know I brought it up last, well, that's just because it's last on the paper, but it really is the first thing you need to look at. Find a cam that gets you close to 7.5 to 1 or greater dynamic compression ratio. On a typical street build, this determine all of the other cam characteristics that you need to suit your needs. Sometimes this requires using a higher static compression ratio than you need to, and can affect how low of an octane gas you can get away with and be safe from detonation. Now, how do we find the effective stroke used in the formula of the engine given a specified intake valve close point? Well, math, of course. Okay. Once you have the effective stroke calculated, next calculate the static compression ratio using the effective stroke number in place of the stroke length. Okay. Okay, sorry, the battery died. Thought I had a good enough charge on it, but anyway, carrying on. So, for example, say you have a small block Chevy bored 40 over, 3 3/4 stroke, intake valve close of 56.2 degrees, 0 deck height, okay, 40 thousandths compressed gasket thickness, 4060 gasket bore, 64 cc chamber, negative 26 cc dish pistons, and a 5.7 rod. Follow the below formula to first calculate the effective stroke and then static compression ratio using the effective stroke in place of the stroke length. Okay, so you're going to need a scientific calculator to do this. So effective stroke, horizontal displacement, okay, 0.5 times the stroke, do that in parentheses, times the sine of intake valve close angle, okay, that's 56.2 degrees. Okay, next, rod displacement below crank center line, half times stroke times the cosine of the intake valve closed. Piston rise from basically these two numbers, okay, RDCL equals piston rise 1, okay, from the rod distance below crank center line is square root, parentheses, the rod length, okay, minus RD2, okay, sorry, squared. You can't do squared on here, so then you have piston rise from crank center line, okay, piston rise 1, piston rise 2, okay, PR1 minus RDCL, okay, effective stroke is going to be accumulation of all these things you just had. The effective stroke is stroke minus, just look, I don't have to read this to you. You can see parentheses, and just make sure you do this correctly with all your parentheses in the right spot. Okay. Static compression ratio, everybody's done this before. Bore squared, gasket bore squared, that's just this 2 is going to be squared, okay guys? Anyway, so you got all these formulas here. If you have trouble with this, just let me know. If you have a graphing calculator or a scientific calculator on the phone, you should be able to do all of this, okay? Or you can just do what I did and do it just one time and have a spreadsheet that'll do it for you. Okay, so this is our example. Now the one thing that I want to make sure I point out, intake valve closing point is not your 50 thousandths intake valve close point. It is the advertised from the manufacturer intake valve close point. Okay, so this camshaft, I think, that I used for this example was a comp cams, and they do most of their stuff at 6/1000ths of lift. Okay, you want to get as close to zero as you can. If you have been able to degree a cam in the engine, you can figure this out for yourself. So anyway, this is just taking all those numbers we just calculated. Okay, these formulas are a little bit easier to read because I was able to actually type them in a formula format. So up here I was just writing them out, so that was a little confusing with the 2's and stuff, but this is better. Okay, bore square times deck height, gasket bore square times gasket thickness, all that kind of good stuff. Okay, RD horizontal, RD center line, PR1. Okay, so look at these, and this is going to be all your formulas to get your effective stroke. Okay, so I'm using 83% of the stroke from the point the intake valve closes to the top of top dead center. Okay, so from the point the intake valve closes completely to top dead center, 83% of the stroke. Now, the reason why this is just a single measure is because you do have inertial filling. So as the intake, or as the piston is moving back to top dead center, again, remember, you still have air and fuel coming into the piston, or into the cylinder. Okay, so just because this says I'm only using 83% does not mean I'm going to have 83% volumetric efficiency. Okay, my new 100% is not now 83%. You will still get greater than this if all the velocities are correct in your intake port. Okay. All right. This is a target boost, so if you're using boost, you'll want to calculate also your effective compression ratio. So 9:1 was a static, dynamic 7.52, and effective 15.2. So 10 pounds of boost on 9:1 static equals 15:1. So this means race gas. Okay. How much race gas you can calculate as well. Anyway, I'm not going to get into that. It's not the purpose of this video. Dynamic compression ratio is what I'm going to get at, 7.5. So this is a good target number. This will be a very good torquey motor on pump gas. Okay, so this is a good setup. All right, so we're gonna go back up here where we talked about our points. All right, we talked about point 16. Okay, intake center line angle. Okay, intake center line describes the point of highest load lift after top dead center. All right, and just to show you on the engine, okay, pull this up again. All right, so we're going, engine's going, boom, we're in the power stroke, exhaust valves open, exhaust valves closing, intake valves opening. Okay, I'm going a little too far here. Alright. Okay, so keep going till we get the peak lift of the valve. Okay, so 595 thousandths, that's after the lash. Okay, that's after the 16 thousandths lash I put in it. Okay, that is going to be the intake center line. Okay, intake center line is the point of the highest intake load lift. Okay, conversely, exhaust center line is going to be the same spot. It's the point at the peak lift for the exhaust valve. Alright, moving on. Alright. Lobe separation angle, it can be found by adding the intake center line and the exhaust center line, then dividing that by 2. Simple. It's a derivative. LSA, people are talking about, oh, I want 112 degrees, or I want 113 degrees lobe center. That's what I need for my engine. Oh, I'm boosted. I need 113, 114, 115 degrees intake or lobe separation angle. False. 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 Do not listen to it. Do not listen to it. That is marketing. Okay? Wider lobe separation angles greater than 112 degrees tend to reduce overlap, have better idle quality, better for EFI tuning, better fuel economy, better idle vacuum for power brakes, flatter torque curve. That's not always 100%. The downside to the wider lobe separation angle is they tend to have reduced low speed torque as well as lower peak torque and tend to favor high RPM horsepower due to the fact that they have a broader torque curve carrying the torque higher into the RPM band. This is not 100% true, this last part. I know I put it in here, but there's exceptions to that. But they do tend to favor high RPM horsepower. Okay? Narrow lobe separation angles less than 112 degrees are just the opposite. They tend to make higher low speed peak torque and have a narrower torque curve. However, they tend to reduce idle vacuum, increase overlap, reduce fuel economy, worse drivability on the street. All that is true. However, they do make more torque. Okay? You ever seen a circle track car or sprint car? They have very, very, very tight lobe separation angles because they need to stay in that mid RPM peak torque area as much as possible. They need it to get out of the curves. Okay, advance and retard. If you advance or retard the camshaft, you can change the intake center line and valve timing events. Advancing the cam tends to act like reducing lobe separation angle, and retarding the cam tends to behave like widening the lobe separation angle. In general, cams tend to come ground with a certain amount of advance already. Check your cam card and always degree your cam. Okay. Old Red's cam, I had it designed with 4 degrees of advance so I can install it straight up, and it already is 4 degrees advance. That's where I wanted it. Okay. I still degreed the cam, and it came in right where it needed to be. Okay. These describe the piston position relative to the bore and is used to describe valve events. Before top dead center, before bottom dead center, after bottom dead center, and after top dead center. Okay, these are pretty intuitive, but usually you'll just see BTDC moving forward. Now that you understand camshaft terminology, we can get into why knowing this is helpful to determining the right cam for your application. First, we will talk about intake center line. To find the optimal intake center line, you will need to choose an intake valve open point and intake duration. It is best to use duration at 50 thousandths lift so that you can look and shop for a cam that is in that area. There is not necessarily a formula to estimate required intake duration to achieve a certain RPM band, and that is due to the fact that there are too many other variables to consider. Cam manufacturers typically provide an estimated optimal power band of a given camshaft they design, but that is because they know the lobe design and other technical factors that we as the consumer do not have access to, and to measure would be very difficult. For example, 2 camshafts can have exact same lift, duration, lobe separation angle, but behave differently because the lobe profile is different. I'll prove this later. CompCam's Master Lobe Book is a powerful tool to choose the right lobe profile for your application. In general, low duration camshafts less than 220 degrees at 50 thousandths are good for idle to 5,500 RPMs. Mid-duration cams, 220 to 240, are good for 2,000 to 6,500 RPMs, and high-duration cams greater than 240 degrees are good for 3,500 to 7,000 RPM. Again, this is very general, and it is best to find several examples for the RPM range that you are targeting. The intake duration also determines the stall of your automatic torque converter needed, but I am not going to get into that here. It is best to call the converter manufacturer for a recommendation, but in general, anything over 215 degrees of duration on the intake usually requires an aftermarket converter. Okay, so once you've determined an intake duration, you need to choose the intake valve open point. Again, intake valve open only affects overlap. For example, if the intake valve is open before top dead center and the exhaust valve is closed at top dead center or after top dead center, the valves will be open at the same time and you will have overlap. How much overlap has the effects discussed already. One more example with actual numbers to illustrate this better. Okay, here we go. Intake valve open, 9 degrees. Exhaust valve closed, 7 degrees after. Okay, this example has 16 degrees overlap. Okay, added degrees, Bravo and Alpha. Okay, you can do this math. Okay, now let's look at choosing the intake center line. Optimal for your choosing duration and intake valve open point. To find this, follow the below formula. Intake center line is intake duration divided by 2 minus intake valve open before top dead center plus intake valve open if after top dead center. So this is either going to be a minus if before top dead center or a plus if after top dead center. Okay, let's add some numbers below. Let's say we have a 230-242 duration split and we are opening the intake valve 9 degrees before top dead center. The optimal intake center line would be intake center line 230 divided by 2 minus 9, or intake center line of 106 degrees. This is based off a 355 small block Chevy, guys. So if a 355 small block Chevy, everyone in the world is going to tell you 108 degrees is the best intake center line. It's not for this specific duration cam. Okay? Every cam is spec'd out to the cylinder head and cam that you are putting in it. There is no general here. Everything has to be calculated. Alright, so I would choose a 106 degree intake center line for my camshaft. However, what if you have no idea what intake center line would be optimal? There is a formula you can use to get you pretty close. Okay? Intake center line equals 128 minus engine size and cubic inch displacement divided by 8 divided by intake valve diameter times 0.91. Okay, this is a well-known formula. Okay, this is not mine. For example, intake center line 128 minus, so we're just going to use a 383 here. 383 divided by 8 divided by 2.02. So if you have a 202 intake valve, which is pretty common for a small block, unless you're getting into the bigger heads, times 0.91, some numbers here, intake center line, 106.43 degrees. This tells me that the above cam specs would be well suited for a 383 small block. I said 355, but if you were using a 350, 108, okay? For this exact intake valve close and this duration cam, sorry I told you wrong earlier, 350, but however, 106 intake center line is what Old Red has, and that is what Old Red needs, okay? It depends on the duration of the cam that you chose and when the intake valve is open, okay? This will be moved. So if you took a 208 valve here, okay, and you put 350 here, I bet you'd be pretty close to that same number, okay? Let's just do it here. So 128 minus 355 divided by 8 divided by 2.08, which is 208 inch intake valve, 0.9 times 0.91. And you would have 107 basically, but anyway, I don't remember the intake valve close point on Old Red right now, but this will change, okay? It will change. So 108 degrees is good for this one on a 350, or 106 for a 383. Alright, if you were to use 350, okay, you can play with this once you have decided on intake valve size and engine size. It will get you very close. Okay, so if you're trying to figure out when you need to open the intake valve, do this formula to tell you the optimal, and then pick an intake valve point and then a duration. Okay, you can change the duration or change the intake valve open point, but I would not do both. Now that you know the desired duration of the intake valve and the intake center line, we need to choose the optimal exhaust center line. Again, you need to decide how much overlap you desire. In a boosted application, close to zero is best in low boost street applications. Increasing overlap tends to favor high RPM power gains at the sacrifice of low speed torque and stoplight drivability. A good rule of thumb for nitrous and supercharged applications is to add 10 to 12 degrees to the chosen intake duration for performance. That is a mistype for me. Exhaust, okay, 10 to 12 degrees on the exhaust side. Okay, this will help give the exhaust more time to scavenge the cylinder before the intake valve opens. You want to add a 10 to 12 degrees extra on the exhaust duration because you have more air fuel mixture in the cylinder. You got to have more time to get that out. For turbo applications, early exhaust valve open can directly affect spool, which requires a good balance of intake valve open and intake valve close. Again, there's a lot to camshaft design, and choosing the right cam for your application takes time. However, choosing the right cam be the difference between 50 horsepower or more gain or 50 horsepower or more loss with terrible drivability. A cool sounding cam does not equal power. Okay, now to calculate exhaust center line. Exhaust duration divided by 2, this is going to look very similar, minus exhaust valve close after top dead center, or plus exhaust valve close if before top dead center. Let's add some numbers, yada yada yada, 114 degrees. Okay, so you can look at those numbers there. Pause the video if you need to look at it closer. So I would choose 114 degree exhaust center line for my cam. Also, you can use the same formula above on intake center line for exhaust center line estimations by using the modified version. Okay, exhaust center line equals 142 minus engine size in cubic inch displacement divided by 8 divided by exhaust valve diameter times 0.91. Okay, put some numbers together, estimate 114 degrees. So it looks like we've chosen the right cam. Now that you've chosen the intake exhaust valve duration and intake center line and exhaust center line, you need to solve for the lobe separation angle. Okay, so all it's going to do, intake center line plus exhaust center line divided by 2, 110 degrees. Okay, a camshaft duration, lobe separation angle, and advance is simply a derivative of choosing 4 valve timing events discussed in point 9. If you are comfortable choosing your own valve timing events, you can do so and see how it affects the rest of the cam specs. As previously discussed, intake valve close is the most important valve timing event. I could explain all the math, but Summit Racing has a good little calculator here for you. Okay, if you want to know how to do the math yourself, I can teach you that, and I may do another video on it, but Summit has their own cam timing tool. Just to type in Summit Racing cam timing tool, and you'll be able to go in there and play with the valve timing events, and it'll see what the duration cam that you really need is. Theirs is based off 50 thousandths. Just remember that. Once a cam's duration, lobe separation angle, and advance has been chosen, it's time to decide how much lift you need and how aggressive you want the lobe to be. There are a lot of considerations here, so let's discuss some of them. What kind of style lifter do you want to use? Hydraulic flat tappet, hydraulic roller, solid flat tappet, or solid roller? What is the lift point at which your cylinder heads run out of flow or become turbulent? How important is valve train life to you? Okay, is this a race car that you don't mind working on often, or is this something you just want to install and leave it alone? What is your budget? Big deal there. Solid roller, very expensive. Okay, hydraulic flat tappet, not expensive. What do you want Do you want a quiet valve train that has low maintenance, or a valve train that is noisy and requires periodic lash checking? Okay, this is true. Okay, my old red is a solid roller, and I have to do this every every 1,000 miles, every 3,000 miles at oil change. You'll have to lash the valves. I enjoy it, so I don't mind it. These are just a few questions you need to answer. The difference between the styles of lifters is well documented, but in general, a solid lifter will tend to allow for greater RPM without encountering valve float, but require checking the valve lash at least every oil change and tend to have noisier operation. A hydraulic lifter will be quieter and require little to no maintenance. However, you will have lifter pump up, and it will not support as high of an RPM. Now, there are very high quality roller hydraulics out there that will get into the higher RPMs, but they are expensive. Okay. It's important to choose wisely, as the option you go with will potentially limit your power potential. For example, if your heads are capable of flowing enough air to support 7,000 RPM on your application at 700 thousandths lift, but you choose a hydraulic flat tappet that limits both the RPM potential and lift at 550 thousandths, then you will never reach the capacity of the heads, and the heads at that point are too big for the application. You could get more power out of a smaller head down low. Another example, if you choose to use a very aggressive solid roller that has 700 thousandths lift on a set of heads that only flows 500 thousandths lift, then you will end up with poor combination, disappointing results, and valve train that will possibly not last long. The best practice to match the cam to the specific usage of the application, RPM range of the heads, and the lift range that matches the best flow area of the heads. For example, if you have a naturally aspirated daily driver that uses EFI on a 350 small block Chevy with a stock 1500 to 2000 RPM stall converter, a set of heads that had an average flow of about 220 CFM and hit the peak flow at 500 inches of lift and the 6,000 RPM max potential based on the flow, minimum cross-sectional area, and port volume, then a good cam choice would be something that had a duration with an RPM band of 1500 to 6,000 RPM, a hydraulic flat or roller tappet on a 112-115 degree lobe separation angle, low overlap with about 4 to 5 degrees pre-ground advance. Lobe selection would need to be the mild in nature, since the car is a daily driver and will see a lot of miles and needs to have good reliability and street manners. If I were to take these specs and look at what is out there on the shelf, I would find thousands of cams. So which should you choose? In reality, many of them will perform similarly, but pay very close attention to intake centerline and intake valve close, as the one that has the earliest intake valve close and optimal intake centerline will perform the best on your combination. What is intake valve close? Why is intake valve close so important? Okay. Alright, so we went over this. We've already talked about that. Alright, okay. So now that you have the tools needed to choose the right cam, timing, lobe separation angle, and the amount of advance or retard required, the last thing you need to choose is a lobe profile. This is where you need a lot of engineering R&D to develop, so we will use existing lobe profiles from the CompCam's master lobe catalog. Some lobes are asymmetrical, meaning they have different ramp rates on the intake valve and the exhaust valve. The intake lobe on the going up ramp and coming down ramp may be different. Okay, the ramp rate going up and is different than the way going down. Remember when we discussed measuring heads with their average flow number? Well, this is how you determine the exact average head flow number. This will require some examples to illustrate, but for a baseline, let's use my recent home ported heads flow bench numbers. Okay, so these are old reds flow bench numbers. They actually flow more than this because I kept working on them after this, but alright, so, and they're not 210, they're 205. This was slapped down pretty quick, but so 210 cc. Just look at the flow numbers on the intake and the exhaust. Okay, this is where it's important. Cross section, okay, cross sectional area, and this is the basically your intake and exhaust ratio. Cross-sectional area is 2.1. That's my minimum cross-sectional area, is 2 100,000ths. Intake valve and exhaust valve. I had a 202 valve. It's now a 208 valve. So this was prior to me making some more changes on these heads. Okay, this is coefficient of discharge, intake, and exhaust. Not going to talk about that on this video. Okay, just focus on the flow numbers for now. Using these numbers, the rough guess on average flow would be 225 CFM using the 200 to 500 lift numbers. Okay, because my camshaft, if you noticed, only goes to 594, so 600 thousandths doesn't even matter. Using these numbers inside of your chosen lift range, also never use the 100 lift values, tend to be inaccurate. Okay, I told you the reason for that. Okay, so here's the meat and potatoes, guys. This is why it matters. To illustrate how we can manipulate this average flow number, which is directly tied to optimal engine RPM with the load profile of the cam, we need to have means of seeing the actual duration at each lift value. How long does it spend at 200 thousandths lift? How long does it spend at 300 thousandths lift? Okay? How many degrees of camshaft or crankshaft rotation am I spending at that specific lift value? Okay? Because the load, blah, blah, blah. This is hard to access. Okay, this is hard without access to software that can visually display the load profile, such as what I'm using to show you the engine is Performance Trends Pro Engine Analyzer. The screenshot is of two camshafts with the exact same specs. Duration, lift, lobe separation angle, advance, everything is exactly the same. They have different profiles on the cam. Because the lobes are designed to ramp differently, the purple lobe has a very aggressive ramp speed, whereas the green lobe is slightly tamer. Since they have the exact same specs, inherently the green lobe has more effective duration. There is power torque difference between the two, which makes sense. The green lobe will make marginally more power up top due to the additional effective duration, and the purple lobe will make more torque down low since the valve opens faster, giving it more low lift flow. The power gain from the green curve doesn't come without a cost though. Both peak and average torque drops, as well as average power and idle vacuum. This is worthwhile. Is this a worthwhile change? That is for you to decide. Okay, I know I'm reading this to you, but it's just to try and keep time down. I'm already going long. Okay, this is a lot of information, guys, and I'm not even getting into all of it. Okay, the below table. Okay, so this is peak torque, average torque, peak horsepower, average horsepower, and RPM. Okay, you can see there was a 4 horsepower increase at peak power, but the average power went down, the average torque and peak torque went down. Is that worth it to you? To me, no, it's not. But somebody who's racing and only cares about peak RPM, they'll care about this. The street guy, he's not going to want that. Okay, look at the load profiles, guys. They don't look super different, but their flow, average flow, is different. Okay, the green lobe is snappier, but has less effective duration at the peak lift value. Okay. The below table shows exactly how long the valve will spend at each lift value for both curves. The degrees of lift point duration are doubled since the valve goes up and back down, and the lobes I have chosen are symmetrical to keep this easy to see. As you can see, the actual average flow is higher than the estimated average we calculated above. We calculated 225 CFM for average. Now, again, guys, it's an exact science. So if you're just doing the averages, if the averages are all various between several different heads that you look at, the higher average is going to be better. This is because I have chosen a slightly aggressive solid roller profile that has a very fast ramp rate, snapping the valve open faster, allowing the valve to be open longer at the top of the lift range for the same given duration. The peak RPM will slightly different in reality because the flow value at 500 thousandths lift is not the same as 550 thousandths lift. But most cylinder head companies will not provide you a very detailed flow sheet. So if you have a flow bench like I do, you could literally you can get really crazy with it and do 100 thousandths, 110 thousandths, 120 thousandths, and go all the way up and get this average flow even more accurate, because at 150 thousandths lift, it's different than 100 thousandths. But for simple viewing purposes on here, I'm just showing you a little bit more accurate than just taking the average flow. If you have access to a flow bench, this can be even more accurately calculated, like I said. However, when you get that detailed, you are not talking much difference, and there will likely be little difference in average flow. If you look at the green cam specs below, you will see that predicted that the peak power RPM within 92 RPM. If you were to get even more detailed with the flow values of smaller increments, you would see that gap close probably. Okay, so the one we're using here, 230, 242, and 108 degree lobe separation angle at 4 degrees advance, and 1.5 ratio rockers. Same exact specs here with a 1.8 ratio rocker. So the lobe itself is less aggressive, but we're using a higher ratio rocker to get the lift. So the lift is exactly the same for both of these cams, but because this one's less aggressive, okay, you're snapping the valve open, okay, and this one has got a much more aggressive lobe with a much higher lobe lift, so you use a lower ratio rocker. Okay, so idle vacuum 12, anything 12 and greater is good for power brakes. Anything less than 12 is not good for power brakes and will require vacuum reservoir. Okay, so idle vacuum's down. Both of them are 20,000 slash. Okay, so the average flow here is 242. Okay, 242. Go down here, 248. So the average flow is higher. The RPM is higher. So you're going to make more power. But because I don't spend as much time down in the mid-lift flows, I'm going to lose torque. Okay? It's just a fact. As you can see, there's more to camshaft selection than just duration and lobe separation angle. Hopefully now you see a direct relationship between cylinder heads and camshafts and why the choice of one directly affects the other. People always talk about stages of cams, hot cams, torque cam, blower cam, turbo cam. That's all crap. Now you see that this is all crap. I even said that here. You do not need a turbo cam for a turbo engine. You need the right cam that matches your entire combination. Okay, so I'm hoping the tools that I provided you here will better educate you, and if you have a specific question about your individual application, just get with me in the comments and I can help you work through it. Alright, that's it. See you guys.